All right, good morning, everybody, and welcome to IGTV. We have with us this morning William H. Murray, and Bill will be talking about the Internet as an infrastructure. Go ahead, Bill.
Morning, Joe.
Good morning.
Today, when one connects an application, system, or network to the public networks, one is adding to the system of public works, that is, to the infrastructure of the nation and the world. The standards for building infrastructure, such as bridges, tunnels, and dams, are different from those for other artifacts. Infrastructure must not fall of its own weight. It should not fall in normal use or under normal load, and must resist easily anticipated abuse and misuse. A suspension bridge must not fall because the driver of an 18-wheeler falls asleep and drives over the edge. Notice that abuse and misuse that can be easily anticipated today is much worse than when we began the Internet. We call the resultant property of infrastructure resiliency rather than security, but the properties are related. However, for any artifact, there are limits to the complexity, scale, load, and simultaneous component failures that the mechanism can be expected to survive. How many sleepy drivers and plunging 18-wheelers must a bridge be designed to survive? When those limits are reached, what we want to happen is that the mechanism fail in such a way that damage is limited and the mechanism can be restored to operation as quickly as possible. The three great northeastern blackouts, of which August 14, 2003 was the latest, are examples. It's interesting that engineers see these blackouts as successes, while the public and their surrogates, journalists and politicians, see them as failures. All three were caused by multiple, simultaneous component failures under conditions of heavy load. In all three cases, the system failed in such a way that it was restored to a 90% service level within a day. While all three were spectacular and exciting, the damage was not nearly so severe as one might expect from a single major ice storm. That's the way we'd like to see the public networks fail. In fact, so far that is what we have seen. We've had massive local failures of the public switch telephone network, Hillsborough and Lower Manhattan, where it took days to weeks to restore to a 90% service level. All of these were fire-related and local. We've had one that was national and caused by a software change. We recovered from this one in hours. To date, we've had a number of local failures of the Internet, all man-made, mostly caused by the infamous cable-seeking backhoes and boat anchors. Most were accidental. We recovered from all of these in days. SQL Slammer was man-made, malicious, and software related. It caused a noticeable drop in service for hours. However, there was never really a discontinuity of service. It should be noted that SQL Slammer was a homogeneous attack. That is, every instance of it looked the same. That made it relatively easy to construct and deploy filters that would resist its flow, while not interfering with normal traffic. However, it's fairly easy to visualize a heterogeneous attack that might overwhelm this particular remedy. So there is widespread concern that there might be a malicious, software-based attack that could bring down the entire Internet. To some degree, this is angst, an unfocused apprehension rooted in intuition or ignorance. However, it is shared by many who are knowledgeable, and concern is rooted in the often unidentified and unenumerated facts that the Internet evolved. It was not designed or deployed. Switching in the network is software-based. Operation of the components is homogeneous. Operation of network management controls and provisioning is in-band. Users often have default access to management controls. The topology is both open and flat. Paths in the network are ad hoc and adaptive. Connection policy is permissive. Most of the nodes in the network are untrusted, and a large number are under malicious control. Access is open and cheap. Identity of both components and users is unreliable. Ownership and management of the internet is decentralized, and there are probably a dozen others that I have not yet identified and enumerated. Now, the impact of these is less than obvious. If it had been obvious, we might have fixed them in the first place. So a little bit of discussion of them is probably appropriate. Unlike the public switch telephone network, the internet is packet rather than circuit switched. The intent of this was to make the network more resilient in the face of node or link failures. The routers and switches may be software running on von Neumann architecture, general purpose computers. This was certainly true in the beginning, a little bit less so now that we are using purpose-built routers. However, this may make the network more resistant to component failure while making the components more vulnerable to malicious attack. We've become accustomed to the idea that software processors are vulnerable to interference or contamination from their data. That is, the software in the switch can be contaminated by its traffic. This exposes us to attacks intended to exploit, interfere with, or take control of switches and routers. This may be aggravated by the fact that so many routers and switches look the same. While there are hundreds of products, most of them present controls that are operated via BGP, the Border Gateway Protocol. An attack that can take control of one might be able to take control of many. Even most non-switch nodes in the network look the same. That is, like Windows or Unix, rather than, for example, MVS or OS 400. These two operating systems, Windows and Unix, are open, historically broken, and have a commitment to backward compatibility that makes them difficult to fix. Historically, they have shipped with unsafe defaults and have been corrupted within minutes of being connected to the internet. The result has been that there are millions of corrupt nodes in the internet that are under the control of malicious actors. Operations of the routers and switches and other network nodes is via the network itself. They can be operated from almost any node in the network. Many are hidden, if at all, only by a password, often weak or even default. Thus, it might be possible to coordinate simultaneous misoperation of many nodes at the same time. The internet is open as to user, attachment, protocol, and application. The cost of a connection to the internet is a function of the bandwidth or load, but the cost of a relatively fast, persistent connection is in the tens of dollars per month, about the same as a 56K dial connection a decade ago. While one must demonstrate the ability to pay, usually with a credit card, the credit card may be stolen, and depending upon the provider, the name in which the connection is registered may not have to be the same as the one on the credit card. In short, almost anyone can add a node to the internet with minimal checks on their identities or bona fides. There will be bad actors. The only thing that is required to add a new protocol or application to the internet is that at least two nodes agree on it and that it can be composed from IP packets. Use of load-intensive protocols and applications for streaming audio and video were added to other protocols and applications with no changes to the underlying infrastructure. We have seen denial of service attacks that relied upon minor changes to protocols and their use. At least in theory, the topology of the internet is flat, as opposed to structured or hierarchical. That is, at least in theory and with few exceptions, any node in the internet can send a packet to any other node in the internet. The time and cost to send a packet between any two nodes chosen at random is roughly the same as for any other pair of nodes. Said another way, both the time and cost to send a packet are independent of distance. One implication of this is that attacks are cheap, can originate anywhere, and can attack anything attached. The paths in the internet are determined late, possibly on a packet-by-packet basis, and adapt to changes in load or control settings. The intent is that there may be so many potential paths between A and B that at least one will always be available, and that it will be discovered and used. While the intent is to make the network resistant to node and link failures, an unintended consequence is that it is difficult to resist the flow of attack traffic. The original policies of the internet were promiscuous as opposed to permissive or restrictive. Not only was any packet and flow permitted, but there were no controls in place to resist them. This was essential to its triumph over competitors like SNA, and may even have been necessary to its success. But while controls have been added as the scale has grown, the policy is still at least permissive rather than restrictive. That is, everything is allowed that is not explicitly forbidden. Said another way, all traffic is presumed to be benign until shown to be otherwise. Attack traffic can flow freely until identified and restricted. Finally, while most of the nodes in the internet are untrusted, and we know that many are corrupt and under hostile control, all are given the benefit of the doubt. To date, there has been little effort to identify and eliminate those that have been corrupted. Therefore, there remains a possibility that these corrupt systems can be marshaled in such a way as to deny the use of the network to all or some targeted group of users, like Estonia or the adversaries of WikiLeaks. All that said, the internet is robust, not fragile. It is resistant to both natural and accidental artificial events. However, to the extent that the above things are and remain true, the internet, and indirectly the nations, economies, institutions, and individuals that rely upon it, are vulnerable to abuse and misuse. Concern is justified, if not proportionate. While these characteristics are pervasive and resistant to change, while they were often chosen for good reason, they are not fixed or required and can be changed. Understanding them and how they might be changed is key to making the internet as resistant to abuse and misuse as it is to component failure or destruction. It suggests that the network must become both less open, not to say closed, and more structured. The management controls must be protected and taken out of band. The policy must become much more restrictive. We must identify our users and customers and hold them accountable for their traffic. To bring the internet to the infrastructure standards, we must overcome not only inertia, but also culture. Each of us must exercise our influence on our employers, clients, and vendors to move the internet to the same standards that we expect of skyscrapers, bridges, tunnels, and dams. Since there is no one else to do it, we are called professionals and are paid the big bucks. See you next week.
Thank you, Bill.